Hi, my name is Ken Hasselson. I wrote the Microbiome Prescription website, and this is a bit of a walkthrough looking at the philosophical and practical issues involved with the microbiome analysis. I'm basically directing it for people who are currently or who are planning to offer lab services for 16 years microbiome or megagenomics. Now, we should understand that there are two parts to it, and I think the next picture will clarify things quite well. The left portion is often the only thing that a lab does, which is take the samples, process it, give the results, gives back a list of bacteria, and that is often it. Often the result of their customer making requests, who typically come back with the question as, is this amount normal or abnormal, etc. And so they go and frequently take off-the-shelf methodologies to determine what a normal range is. What I want to do in this talk is walk through each of these layers and the issues. The issues with what decisions has to be examined, mistakes that can easily be made, and that thing is doing a analysis or evaluation of how well all of these components, which you may or may not choose to add to your existing lab system, or if you're a researcher, do yourself, how to do the evaluation, whether or not you are on the mark, or you're missing the mark, or missing the mark horribly. So let's talk about things. First of all, determining whether or not a range of a particular bacteria is of concern and should be modified. If it's ain't broken, don't fix it. Second part is whether or not you have a diagnosis selection. And that means we know from U.S. Library of Medicine that there are many bacteria shifts which seems to match up with a particular diagnosis. And I have done a selected extract of a variety of conditions here. And if you go to the site, you'll find a list of citations as to where the information is coming from. And you can also see which bacteria are the ones associated with something like celiac disease. And you'll find all the bacteria associated with it, and as well as the medical literature where this information was reported. So if you have a diagnosis or disease, you are now able to shortlist which bacteria are likely to be important for the treatment of this particular condition or disease. If you have the information as to which bacteria, then the question is to look at the samples and determine which bacteria matches that, are desired to be altered to raise or to lower so that you contradict what is found. Typically, experience from feedback from professionals has been that you alter the microbiome and the symptoms are reduced or disappear, because the microbiome and the symptoms seem to have a very strong correlation, which is nice because it means the root cause of the symptoms is not necessarily the disease, it's the microbiome shift that the disease caused. So you now know which bacteria to alter. Do you do it by diet? Do you do it by supplements? Do you do it by drugs? And then last thing comes to performance evaluation. How well have your suggestions of what to take perform against a client base? There are problems all the way through. Now, if we hop back to diagnosis selection, if we don't have it, then you need to go directly to how do you select the bacteria, which bacteria are abnormal or not. You don't have the advantage of studies to filter out. You are in a wild. Do you go north, south, east, west? Do you start digging a hole, or do you start building a hot air balloon? That is the harder case, which is if you don't have the ability to filter out which bacteria are significant, but somebody just feeling odd or wants to improve things, or there's no studies done on it. Then the issue is how to determine which bacteria. So let's go through and start going through all of this bit of absolutely delightful learning. What I want to do is start with a basic review of what is generally done in terms of clinical lab results. If you have run clinical labs or your staff has come from there, chances are they are going to be predisposed to thinking about the data in one particular way. And the way is a very simple one. It's a bell curve, the standard number distribution. The bell curve has an interesting characteristic, or some interesting characteristic, which, as a professional statistician, there is a real easy way to test to see whether or not it is or isn't a bell curve. And that is, there are three measures which should all give almost the same value. The first measure is that the average of all the values should be right here at the very top of the bell curve. Second one is that your median, the value of which half the population is below and half the population is above, should be almost identical to the average. The third one is the most common value should also be about the same as the average and the median. In other words, everybody sits right around here. If that happens, you likely have a bell curve, maybe skewed or whatever, but it is more reasonably likely to have a bell curve. If those are false or extremely false, you don't have a bell curve. You cannot use standard lab procedure of calculating the median, standard deviation, and making a pronouncement that anything more than 2 standard deviations above the mean or everything 2 standard deviations below the mean is abnormal. It's not correct. It is totally wrong statistically, and you need to do some upgrade of your statistical skills. When we go over and look at the microbiome samples, here is one in front of you, and this is based on, this is a very old sample. At that point in time, it was only 1,000 samples. We're up to 2,000, but the curve stays the same. And we'll see what the count is and the percentile here. So with this type of chart, the 50th percentile is right there. The median is where it's supposed to be because it's by definition at that point. But so now where's the average? The average is up here at 72%. In other words, 72% of people will have a value below the average, and 28% of people will have a value above the average. Ooh, that doesn't quite sound what you were expecting. How about the most common value? Oh, it's down here at the 8th percentile. In other words, the most common value, the one that most people have, is sitting down here at 8th percentile. We have 72, we have 8 right there. What in the world is an abnormal value here? This is the problem. What we find is that the statistics for still microbiome analysis is, excuse the expression or pun, a pain in the posterior. And we have this one. When I first came across this data, I sort of said, oh, okay, forget about using the standard performa. A statistician, I looked at the data and says, wait a minute, data doesn't fit. Assumptions are wrong. And let's try understanding what's going on here. I have many professional data scientists and statisticians as friends, and I showed the curve to them, and they tossed me over to some economic data, which we also don't have a bell curve. Here is income distribution per percentile, and it looks almost like a microbiome. Wait a minute, isn't a microbiome a population of bacteria? Here we have a population of people, and we almost end up with the same curve. Strange. Almost as if there's a natural process involved. And often you will hear people talking about average income and median income. The average income and the median income for the U.S. population is different. I think the average income is something like 70%, and the average is, average is 70, and the median is down here at 50, and the most common is actually lower there. So we almost have the same type of skewed data, which indicates it's not a bell curve. However, the same people were quick to point out to me that if you do something called logistic analysis or other things, you end up changing the curve into something which actually is more interesting to work with, as in you have here generally a flat middle section which is quote normal, and then you have things curving away from it, which we call inflection points, and there's a methodology which can be used called the Coulter-Moultrie algorithm, which helps determine outliers by using this type of data analysis. So what does it look like when we apply the same thinking to the microbiome? We end up with actually something even more interesting with some of the mathematical function application. Again, across the bottom we have percentile, and what we now find is we find for the majority of the population we have a straight line. Straight lines are always frightening because it indicates that however the process is going, it's a linearity to it. There's no oddity. But we do notice that at the top and the bottom we have sudden changes, which the straight line ceases being a straight line. And using this approach, we can see that the average is up here at 75 percentile. The mode most common is here at 12% for just one. Of course, the median 50 percentile is where it always is. But we can now say from the data, if somebody has a value here or above, it looks abnormal. Or value here or below, it looks abnormal. Here and above seems to be around the top 2%. Down here is probably around the bottom 3 to 4%. And the catch is these curve points differ from bacteria to bacteria, which means you can't just do a abstract. Okay, we'll do top 2 percentile, bottom 2 percentile. You have to examine it bacteria by bacteria to determine where the abnormalities are happening. So this is coming from the Coulter-Moultrie, which is what I tend to use on my side. It is a proprietary mechanism, algorithms, etc. But I should go on to look at the alternative way, which is often being used, which is conceptually a good choice. I tried using it originally on my site and I wasn't happy with the results, but I should at least show you what it is and explain the problem. And it's using quantiles or boxes. It's a standard data science method. It's pretty good. Works 80-90% of the time. 80-90% of the time is generally a happy numbers for data scientists. Unfortunately, the microbiome doesn't fit into that 80-90% of the time. And what you will find in many studies, you will find they will show you a chart using boxes as shown here. And the chart is very easy to understand. The line in the middle here is the 50th percentile, which we should be familiar with, called the median. Bottom line is the 25th percentile, or Q1, and top line is the 75th percentile, Q3. So 50% of all samples are sitting in here. Up here is a line which is calculated by a formula which comes from basically ad hoc experience, and then we have the outliers above it. Some cases you can see there's just a few outliers. Other cases you can see that, wait a minute, just about everybody has the same value, and we have a bunch of outliers. Here we have a large number of outliers. Here's another chart below, and you can see who are outliers and who are not. It tends to be, I view it as being slightly unreliable. But let's go down and look at some of the issues. The first issue is some people and some labs I've seen basically deem abnormal to be anything outside the 25th to 75th percentile. Very conservative, but there's a slight problem with that. In this range, 50% of the samples are going to be, that's normal. But that means that 50% of the samples are going to be abnormal. You've got 800 bacteria, you could find 400 bacteria are identified as being abnormal, hence something you should fix, something you should rectify, something that needs improvement. I have a I don't deem that to be a credible statement, because you are basically tossing coins and giving medical advice based on the toss of a coin. Not wise, not responsible, etc. If you look at the ways of identifying outliers with this method, and you can read more on the box plots here. It's a standard data science technique. Then you see who the outliers are. Okay, here we hit some interesting problems. First of all, we have the problem which I mentioned about is that of working with averages and medians, and you guarantee 50% being outliers. Now, if you go and use a more sophisticated formula, you have a problem when only 20% of a particular bacteria shows up in tests. Not unusual. I find it very often. Generally 16 to what is it? Generally 16 to 25% of the bacteria would fall into this rarity factor. So now the question is, how do you treat these values? If they are not missing, then they do definitely have a value. The value is 0. So let's apply the rule above. First of all, quantile 1 is 0 because 75 or 80% don't have a value, or have a value of 0, correction. And you have at Q3, 75 percentile, that's still below the 20% that have values, so that is also 0. So you have both Q1 and Q3 at 0. You apply the formula to determine outlier, and guess what? The high boundary for outlier is 0, which means that every person who has this bacteria reported is abnormal. Every single one, because that's what the mathematics would suggest to it. And that I have a problem with credibility again. For some bacteria, like a rickettsia infection or cholera, then having a presence indicating that you're unhealthy is legitimate, etc. But for an arbitrary bacteria, which we have no associations to any medical condition, to deem that to be abnormal and need to be addressed, just doesn't buy it with me. So that's the issue of finding the ranges. You need to figure out how you're going to find the ranges. I've covered the two typical ways of doing it. One is the bell curve, which is totally wrong. Second one is the boxing, which has problems to it because of the fact that you have 0 values which could dominate some bacteria, and what do you do with them, etc. The third way, which is proprietary Kalthoff Moultrie, is what I use. There are other ways out there. You should not be using the box plot type or the normal distribution curve. Both of them are clearly erroneous to be using. You have to figure out and demonstrate with reliability that you are doing a reasonable criteria for selecting what the outliers are. And that generally means coming up with the algorithm, examining the chart, and seeing if it's logical, reasonable, or credible for the range of values you come up with. So the aspect is we have covered abnormal ranges, and diagnosis selection is somewhat easier because often the information we have from PubMed indicates higher value or lower value, which means you can just do a simple criteria as does this person is above the first quantile or not for this particular bacteria, or below the first quantile. And that is a reasonable matching criteria. But if you don't have a diagnosis to filter through, you are stuck going directly across, and then you really are in a quagmire as to what are healthy ranges. And bell curve and box plot do not produce good results. They produce lousy results. So now move on to altering. We have selected the bacteria to alter. Now you want to figure out how are we going to altering. And we do find that the U.S. National Library of Medicine has many studies finding how a supplement, a diet, a food type impacts the microbiome and which bacteria are shifted by it. So now we need to go and look at those studies and figure out what data is usable from those studies. And that is actually not a simple solution as one would think. You're not just looking up, okay, here. In one way, we don't have that many studies. In another way, we have lots of studies, but they are very diverse. And the diversion of approach and difference of how to report results becomes a real problem of trying to figure out what the actual impact is on different bacteria. So the first question is, which studies from the U.S. National Library of Medicine do you make use of to find the information? Or whatever data source you are using, like Cochrane's, etc. So the first question you have is, how do they determine which bacteria are shifted? And we actually have three major ways of doing it. Each ways have positive and negative aspects for accuracy and the resolution of bacteria impact. We have a culture sample, which is very old school, and you put the sample in, you culture it, and you do a count, a visual count often, of what bacteria shows up, and you do a visual identification. It's was state of the art once upon a time. It's moved on. We have a 16S sample, which uses RNA amplification. It is a cheap way of doing it, and because it's cheap, it's often used in research studies to save money. For some reason, we don't fund researchers well. And then we have metagenomics, which are the upper end, which actually does a full, if you care to think of it, a full DNA analysis of all the bacteria in the sample, including catching, by the way, fungi, virus, and anything else that happens to be in the sample, the stool sample. So you go in there and you find each study does things using a different way of measurement. The question is, how much weight should you give to each result? This one is something you have high confidence of, let's say value of 1. This one you should give low confidence because the methodology is not ideal. So that's the first question, is you have to read the study to find out how they determine which bacteria are being altered by whatever you're giving. For example, could be barley, could be soy, could be a particular antibiotic, could be a particular things for drug for diabetes or high blood pressure, each of which alters the microbiome. Then you come in and you end up saying, okay, oh, wait a minute. This study was done on mice. This study was done on rats. This study was done on pigs, cows, horses, dogs. In some cases, fish, zebrafish in particular. So the question is, which studies do you include or exclude? You could be naive and say, well, a microbiome is a microbiome, therefore it doesn't matter, we use all of them. Other people will dispute that. I won't go into the reason to dispute that, except it is stretching things a bit to infer the response of a supplement to a fish would also be a confident suggestion for a human. We also have some cases, some studies are done with chemical reactors, which are basically big glorified test tubes or things which simulate some sort of living creature environment, ideally the human or whatever, attempts to simulate. It's never 100% true simulation. It's to a certain percentage. The problem is what is omitted may be a significant factor, so it cannot be guaranteed to also apply for humans. Then if you go and say, okay, let's just look at the human studies, you got a variety of issues dealing with ethnic groups, which actually, for example, involves DNA. Lactic intolerance varies by ethnic group. Scandinavians have a high degree, Chinese have a very low degree, similar with alcohol intolerance. So the DNA has an impact on the microbiome and how the microbiome reacts. So the ethnic group is the first question. Gender is another one. The male and the female are different, and I recently saw studies finding that for things like hyperthyroidism, that the female microbiome may account for why hyperthyroidism is higher in females than males. Interesting discovery, but there. Location, which generally can be used as a proxy for diet. If you are doing a study in China, it's probably a far more Chinese style of diet than in the US. If you're looking at the study being done in, let's say, the Northwest, where you have a lot of organic health food things, or you're looking at Alabama, where health food is not a question, just put on another ribeye steak, you're going to get different impacts because the base bacteria is going to be different for each group. Age. We know that children, adults, and elderly often have different responses. For a child, it may increase the bacteria. For an elderly, it may decrease the bacteria. So that's another factor to come in. And more importantly, often the clinical study was done of a cohort with a particular condition and see what the impact is. So you have your controls and you have your cohort. Both of them are given a supplement, and you see how does the supplement change, and you're looking for changes which are different from the control group in the cohort. So the result is you go into the study and now you find all of these complexities. Not only that, but now if you want to go on further and go through the formal process, we have all sorts of questions as to should be asked about the study. And I have 3 links here: how to evaluate and understand clinical trials, the quality, etc. So the result is you may end up having to assign a weighting value for every single clinical study based on all of these factors. How much, and the weighing factor is in some sense how much credibility or confidence you have that this information will apply to a generic human being in your client base. If your client base is the US, you will probably go one way. If your client base is India or South America, probably need different numbers. Now you have the whole assortment of studies, dozens and dozens. Actually, if you go wholehearted like I did, you have probably 3,000 studies. Now you have to aggregate it, and we have a variety of methodologies out there published on how to aggregate. I won't dwell on them, but how you aggregate it is not just adding together. There's more complexities to it, and you probably need to get into it there. And my suggestion is hire a PhD student for a year to help you go through all of this material. It gets messy, it gets technical. Undergraduates don't usually have the thinking skills to want to do it, and not every PhD will, but you're also better with a PhD student. So hire a PhD student for a year, or for a summer, or for a few months. And so the bottom line is you got all these studies through, which are studies which indicate some substance causes some type of shift in the bacteria. So now you have a whole long list of substances and bacteria shifts. Now you have the joy of saying, okay, so I have 5 bacteria, to make it very simple. 5 is actually a small number. 5 bacteria I want to shift. This one I want to go down, this one I want to go down, these 3 I want to go up. Some of the substances going to affect this in the right way, this is in the wrong way, this in the wrong way, this in the right way. So now you got what's in my academic training is called the optimization problem of having to figure out which substances of the possible substances are likely to be a good match. Those of you who have used the system know that I have done what are called safest lists, which are things which impact, if you have 5 bacteria with a particular mixture, everything on my preferred greatest list or ones which have actually no impact on each one of them or the right impact on each of them. So you have to sort all of those things out through all of your studies, through all your bacteria, and it's a good number. My database currently has over 1 million relationships sitting in there. So you end up having to do a bit of data processing, a bit of optimization to resolve it. So that takes you to the point of view of having a list of substances that will modify a bacteria. You know which bacteria you want to modify. Now you have to optimize. You have to figure out what is the right combination, taking into account all the factors. Don't be tunnel vision saying, okay, I want to change just one. Soy increases my bifidobacterium. Okay, that's it. So we go with soy. Except that there's 4 other bacteria you want to change, and soy may adversely affect each one of those 4. You have to take all the information in and balance out and consider all the interactions between all the substances and all the bacteria. As I said, I got over 1 million relationships in my database which is being used. It takes effort to sort that out, and it's fun. And trying to find the right way. Now, at this point in time, let's flip back. We have identified a bacteria to alter. We have built up, hopefully, a good dictionary or library of foods that alters or enrich bacteria, so that we can now go and make suggestions of how to modify things. The last step is an interesting one, which is actually, I would say, far more critical, which is you have all of this work, you have all the evaluations. The question is it right? It may be academically right, it may be logically right, but does it actually reflect the human experience, which is actually the bottom line? Does a human respond appropriately to things? Or a person with particular medical conditions respond appropriately to things. This is something which I have constantly done in order to validate my algorithms in my blog posts looking at individual microbiome. And it is a very simple process. What you want to do is I actually have somebody where you do have a diagnostic selection involved, such as, for example, the 2 I use most heavily are autism and chronic fatigue syndrome. To go look at the suggestions being made, check the literature, and see if the literature for what helps a person with autism or chronic fatigue syndrome is in agreement with the suggestions or disagreement. If they are in agreement, or we have no information from the medical literature, in other words, this thing has never been tried, then you have probably done things reasonably correctly. If you are a medical practitioner, the things that have never been tested and on that list are things that are excellent candidates for treating whatever conditions or diagnosis you're doing. They are things worthy of doing at least a short trial of it. Again, it depends whether or not your results have been performing. Okay, validation methodology with the microbiome is different than usual clinical studies. Clinical studies usually involve using a cohort with a particular medical condition. You obtain measurements of the cohort and match controls. You give them an item for n weeks. You remeasure and you publish results. You now have a nice study, you get brownie points, and hopefully you get a promotion. With microbiome, it doesn't work that way because you're dealing with the microbiome and trying to find a cohort of people with the same microbiome and the same medical condition is going to be a challenge, to put it mildly. It's like saying, okay, I want people with Crohn's disease, but it all must match this DNA profile. You won't necessarily, you may be able to get partial matching for a particular set of defects which are associated with Crohn's disease, but it's going to be messy. So the question is, you have develop your own algorithms for determining which bacteria are significant. You develop your own algorithms for determining which supplements or nutritional elements are going to be able to modify a person's bacteria. And you have developed your own algorithms for determining how to balance out conflicts in supplements or other things in terms of correcting the microbiome. Free proprietary algorithms, which you probably need to write or investigate. Do not go cheap and go for the simplest thing. Bottom line is, you apply all three of them. How do you know that you have the right answer? How do you know if you have a credible answer? Oh, well, you could go down the salesmanship way and say, well, we got positive feedback from users. Okay, positive feedback may mean that it only worked for 10% of the people. It does wonders for marketing, but doesn't really answer the objective question. How do you evaluate it? The model which I tend to use is we do, and it's slower, and you can do it in bulk, but in general what we do is somebody with a particular known condition offers the microbiome sample for analysis as a public blog post, which is up on the blog microbiomeprescription.com. And I go in, I do it, and I see what suggestions are. And often what I will then do is I'll take the suggestions, go over to PubMed, and see whether or not the items suggested have been studied in a clinical trial on PubMed. Often they will, perhaps anywhere between 30 and 60% of the time. The criteria is simple. If I suggest a substance and it's being studied on PubMed and it has a positive effect for this condition, then that is a +1, as in, okay, looking at the microbiome, it suggests this substance would help, and clinical studies found that it helped. So you go down the list and you work through, being aware that some substances, some studies on PubMed may only have a 80% positive reaction, 5% adverse reaction, and 15% none. And that, with the microbiome perspective, is not to be unexpected for some reason that each person's microbiome is distinct, and the study did not control for change for difference of microbiome. But in general, you want the substance being suggested and the clinical study to have the clinical study results showing that for the majority of patients it helps them, and you have to just match up, and you are ad hoc evaluating the accuracy of your suggestions for what should help the person. And you go down the list. If you are a medical professional and you see, okay, yes, that works, that works, that works, that works, this other them, I can't find it on PubMed. It becomes an interesting candidate substance to give a trial to. That's one of the interesting aspects of working with the microbiome, is you can use it to actually mind or deep mind existing for new substances to try, or some cases to be surprised that old substance shows up. One case that quite amused me or delighted me, depending on your perspective, was for a person with chronic fatigue syndrome. And the person happens to be in a situation that he asked the question, okay, which antibiotics or prescription drugs could possibly help alter my microbiome? Most people don't have that luxury of being able to arrange off-label usage of antibiotics or other things. He was. So I ran it through, and I have a couple of thousand, I think I have probably 1,000 or 2,000 prescription items in the database I ran through. And the first 3 items in the list I was slightly amused with. It was 3 particular antibiotics which have been used by several different specialists in ME/CFS to improve symptoms of people with chronic fatigue syndrome. And they were sitting right there at the top of the list, and then everything else was way, way down. Some of the items which I know had been tried with poor results were either on the to be avoided list or were very low value. In other words, from the microbiome, we end up having the joys of getting reasonable prediction. I also repeated that for that particular study, or that particular case, chronic fatigue syndrome, I went over and used the PubMed shifts being reported, the ones which there are agreements on, put those through, again looking at antibiotics, and very similar results came in, as in the preferred antibiotics to treat it, or not for treating an infection but for altering the microbiome, happens to agree with the ones which clinical studies have found have a high probability of success, particularly Dr. Zardine's protocol, who is a surgeon in South Africa, who learned her protocol from the Pasteur Institute of Tropical Medicine, where her father used to work. And it's a matchup, which I find delightful. It means that, for me, it means I have confidence that all my proprietary algorithms through the pipeline are producing a net correct result. May not be perfect. Hopefully you will be better than mine, but it does produce reasonable results that agree with clinical studies. That's how you do the validation. Do the suggestions agree or do not agree with clinical trials? You find people with a particular condition or a group of them, put them through and see what happens. Or alternatively, you create a synthetic microbiome sample using the information from PubMed as to what bacteria shifts, and see if the suggestions coming out of them agrees with studies on people with the same conditions. And if they agree, you have reasonably good algorithms involved. If they don't agree, you probably need to revisit each one of the steps to get a better solution. Okay, so that basically takes you through the process. Let's just do a quick recap. The first part is something which assume you are doing yourself, or you farm out to a commercial lab to do. The first issue is determining what the abnormal ranges are. If you have access to diagnosis which are reliable, you could use that to filter the bacteria to only the ones which have been shown in studies to appear to be significant. If you're not, you have to determine what the abnormal ranges are. The two classic ways of doing it, assuming it's a bell curve, using the box plot method, are both invalid. They should not be used. You're doing bad science if you make use of either of them. So you have to determine what your abnormal ranges are. Once you determine what they are, then you have to determine which bacteria to alter the range. There you get even more complexity. Do you treat all bacteria equal, or do you focus on what percentage change away from your desired level of bacteria is, or do you do by the actual count? Two different ways, as in one is, oh, you 10% overweight, or you 2 tons overweight. How do you determine how much of the variation is significant, and how much weight do you give to the variation? That is another aspect of it. You've determined the bacteria to alter levels. You hopefully have some measure of how much you want, or you could do a simple increase, decrease, and I don't care anything else. You now get your list of substances using your forecasting methodology based on all clinical studies or published studies, and you get your suggestions. You could wait until you get feedback, which is generally unreliable, or two, you can go over and look at clinical studies for people with the same diagnosis and see whether or not the substances you're suggesting are in agreement with clinical studies as things that help. If they are in agreement, you have good algorithm. If they are in disagreement, something is wrong and it's not in the state of Denmark. It's probably in your own kitchen. And if you are MD or researcher type, the algorithm can now be used to suggest alternative substances or drugs or even diet changes to treat a condition. And most of the time, many symptoms of conditions are a result of the microbiome, or the microbiome provides the chemicals to fuel the medical condition. So if you calm down the microbiome so it stops producing the wrong stuff or starts producing the right stuff, then the condition improves. Okay, that's basically it. It was a walkthrough of all these aspects. I've made my own decisions how to calculate each one of these, and if you explore the microbiome prescription site, you can see I give people choices for how to do things. I don't know what the perfect solution is. I have what I found seems to work, and which in terms of performance evaluation, I've been happy with the results. That's the basic criteria. If your predictions don't produce results that agree with clinical studies, then there's a problem. If they do, you are at least in the right ballpark.